talk about proving things today. All right, one of the businesses of mathematicians is to think about and study when to things, to objects, to expressions, to figures in geometry are the same. And so a lot of times we're dealing with two expressions like all the ones we have written here on the board, for example. And you may not realize that actually the thing you're dealing with, the object you're dealing with, is really just the tangent function. And so we started this discussion yesterday. Our goal today would be to prove two expressions are equal to each other. And so this is one we'll do in a minute here. And you can see that those two are not necessarily, one is not necessarily simpler than the other, but this is the one we're going to start by proving. And we're going to show that these two actually do, this equality does actually hold. So that's the one we'll do in a minute. But I just want to kind of set the stage. Really, proving identities, I think you'll find to be, if you liked last night, and some of this is kind of like a puzzle, you'll feel that tonight too. I think you'll enjoy this. I think everyone looks back at their trait identity proving experience in high school with like a great fondness. So this is that moment for you. Just keep in mind that like someday you will look back on this and cherish this. Okay, that's true. I think for anyone at all, as they think back to their trait experience, they're like, oh, I love proving trait identities. Just go ahead, ask your friends and relatives. Okay. And also there are a couple places throughout the high school curriculum where it seems like it's very appropriate to like use the current area of study as a vehicle for teaching you proof and like getting you good at like proof technique and the creativity that's involved. And this is a great place for it. It really is. So I'll start with some hints. Though it might actually be better to show you these hints after you've done one or two so you understand why these are good hints. But the first one's not hard to understand why that's a good hint. If there is a more difficult side, then start with it. It's not always true, like the example I just showed you that we're going to start with. That doesn't have a more complicated side. So that maybe that particular tip doesn't help us too much there. But if there is a more complicated side, by all means, start with it. If someone asks you to prove that tan x over cosecant squared x plus tan x over secant squared x equals tangent, don't start by saying, well, let's start with tangent and unpack that and see if we can turn tangent into this. Probably not the best strategy. You're probably going to start with this nasty expression and we'll reduce it to tangent, right? So if there's a more complicated side, start with it. The second one is kind of us declaring bankruptcy in some ways, right? Like if necessary, feel free to convert just everything to sines and cosines and apply your strong algebra to it. Just go. Let's just do algebra. You saw in the warm-up how fruitful this third strategy is, combining fractions. And already yesterday we saw this fourth one, this idea of setting up a difference of squares in order to help us see some Pythagorean triples. Pythagorean identities. Do you remember that in I think it was the third example on one of the slides I put up yesterday, where we actually used that identity. We were like, okay, hey, we can actually factor this as difference of squares, and then something nice cancels out. And you felt that happen maybe in the homework too somewhere. I don't know where, but you'll see that particular factorization pattern shows up in nice ways in our study of these expressions. Keep in mind that this, unlike last night, is not a simplified task. It's not necessarily true that we're going to take one of the two expressions and simplify it, though there will be that along the way. Really, the goal, of course, keep the goal in mind, is to manipulate one expression so that it looks like the other. So don't ever lose sight of your goal. It's not necessarily to simplify, it might be in some ways making it more complicated too, I don't know. But favor whatever algebraic manipulations that bring you closer to the other side of the equality. What's the last tip? If necessary, work on both sides. And by that I do not mean do things across the equal side. I don't mean that. I mean you can work on one side of the that's reported identity on its own, and work on the other side on its own and see if they're equal. That's fine. But what you may never do, and I think I've said this many times now, is you may never be like, well, here's a thing that's that I need to prove is true. Let's start by assuming that it's true and multiply both sides by 2 or something. Let's multiply both sides by sine x. Not allowed, right? Because again, you're begging the question there. That's a fallacy. You can't start by assuming the thing you want to prove is true to be already true. So don't do that. In general, we'll try to avoid working with both expressions. We'll just try to work with one expression and manipulate it until it is the other expression. And then we'll be done. We'll walk away. So with that in mind, it's really just like the last night's homework with like an answer key built in, right? It's like manipulate this expression. Maybe we'll start with the left-hand side of this. Manipulate this expression and just like make sure you get this, you know? So it's in some ways it's nicer than last night because, well, like I said, there's like kind of a built-in answer key. So again, the first thing you're not allowed to do, I know it's tempting, but it's to be like, multiply both sides by sine x or sine theta. That would be illegal, right? You're not allowed to do that kind of thing. We're going to pick one side to work on, only one side. So which one would you like? How about the left-hand side? They're equally interesting, and so I'm actually going to use that abbreviation, and we'll all agree that we know what that means. That means left-hand side. Is equal to secant squared theta minus 1 over sine theta. And then what I want to do is I want to like add a step here. I want to do algebra to this, whatever it takes to manipulate this, until this chain of equalities arrives at the expression that's sitting on the right side. So your first move. We'll time you here. Take 30 seconds to just struggle with it for yourself. Think about it and see if you can get what you think at least the next step is. Some of you may already like see the way home all the way. At this point, you still may need to refer to your sheet. It's okay. At this point, you need to see anything nice staring you in the face. We will let you have it. Okay, 30 seconds is up. All right, give me at least the first step. What do you notice that's nice? Maybe, I don't know, in the numerator of the expression that's currently written on the board. Varun, take it away. You got it? Okay. What's your next thought? Anyone already have a next thought? Daniel. What's your motivation for that? Yeah, okay, well, one valid reason is because, like, I didn't know what else to do. Sine squared, I guess, is what you meant, right? Yeah. Okay. Is I didn't know what else to do. That's valid. Just do something. It also occurs to me that in the target expression, there is no tangent function, so maybe we'd like to get rid of it, somehow, and make that go away. Good, and then maybe do some algebra to that, just to clean that up a little bit. So what does that come out to there? We cancel anything out. How do we deal with a fraction? Within a fraction, help me out, Kristen.
So like it would also be equal to sine theta over cosine squared theta.
Yeah.
Because like the sine, the denominator cancels out like one of the two signs in the numerator. There's just one sign, but there's still two there's still a cosine squared in the denominator.
Yeah, what she said. And then we're done, right? I mean, we really are though, because
Oh, well, we can break the factor data to 1 minus data.
again, here's an example where like, why in the world would you ever do that? Normally, well, you probably wouldn't, but again, we're targeting the end expression here, and that's where we wanted to go. It's not necessarily simpler. I mean, arguably, this or maybe this is simpler, right? We could have maybe done, if we were in simplify mode, like, I don't know, maybe we would have stopped here or here, you know? But we are trying to get to this end expression, which we now have actually arrived at. So what we've demonstrated here is we have a chain of equalities that shows that left-hand side equals this, which equals this, which equals this, which equals this, which equals the right-hand side. So that is, in fact, what was to be demonstrated. Anyone know Latin? Tell me what that stands for. You know what that is? Come on, there's some nerdy people in here. You know what QED stands for? So far, so good. Yeah.
Est.
No.
Oh, okay.
It stands for quote erat demonstrandum, which is Latin for which was to be demonstrated. So grammatically, why does that make sense to say that at the end of a proof? Well, it makes sense to say the left-hand side equals this, which equals this, which equals this, which equals the right-hand side, which was to be demonstrated, right? So a lot of times we'll write QED at the end of a proof, or sometimes we'll use this symbol, just a shaded rectangle, which means QED also. Mathematicians, you'll see that in, maybe you've seen that before, I don't know, in a math textbook or something. A little darkened rectangle. Or sometimes you'll say, you can actually write out which was to be demonstrated, or you could write out as desired. You don't have to write these, but it does give you like extra style points, like a cool factor that is like not quantified at all by points. Right, like this equals this, which equals this, as desired, right? It's a sentence. This is really a sentence, isn't it? Okay, and that's like the last part of the sentence. There are lots of, you could say, and the proof is complete, or something, or whatever. Yeah. Yeah, do you know what the 3 dots mean? Yeah, therefore. So that's not a great way to conclude something with the word therefore. But you could say like something like therefore, you know, the claim has been established or something like that, you know. Let's try another one. This is good for you. Yeah, Crystal.
Alright, so if both sides of the equation like are difficult, then do you just like pick one?
Pick one.
Or do you like?
Oh yeah, you could work on one and work on the other separately. Yeah, that's fine. Again, you can't cross the equal sign though. Let's make sure we're clear on that. There will be one of you. Where's my money? I'll put $1. I'll put $1 on that right now. There will be one of you who tries to work across the equal sign. I don't know. I would win. I'm gonna win.
So you start with the more difficult.
Yeah, which is the more difficult side here? I don't know. What do you think? Maybe the left side. I don't know. And maybe our goal would be to like kind of get this in product form instead of like difference form. How can we do that? By the way, it's always good to, I think, step back from these and just be like, oh, if that's, it's also really just cool that that's true. Like the tan squared minus sine squared is equal to tan squared times sine squared. That's really interesting. All right, now let's prove it. It's good to like step back and just appreciate it. Again, I'll give you 30 seconds to struggle. Get 30 seconds. 35 seconds. It's great for like puzzles. first step? Give me a helpful first step. I'm ready. That was more than 30 seconds. You should have it. All right, here we go. I think some people said the left-hand side would be a good thing to work with. So I think I like that idea too. But no rule though. I think you'd be equally successful if you start with the right-hand side. So give me a helpful first move that seemed to be helpful. There are a couple things you could do here, but Lauren wants in on this. Go ahead. Oh, yeah, I'm with you. So this is sine squared over cosine squared. Let's make that revelation. Okay. I think that's good. And then you could like factor out the sine squared kind of. Or what did you say? You said sine squared. You put a cosine squared underneath of this? Okay, and combine those two or something? Trying to think what. Yeah, cosine squared. I think I like that. Sine squared minus sine squared cosine squared. So you get sine squared, okay, times 1 minus. Okay, we'll do it your way. Okay. So sine squared. So she's saying write both of these as with a denominator of cosine squared. She's employing the combined fractions strategy. Is that what you guys did? And then you said factor out the sine squared? Okay. Okay. I think I see the I think I see the way rest of where she's gonna go with this. Do you? Yeah, so that's a tan squared. I don't. Maybe we can just do this in one step, huh? And that's a sine squared. Oh, theta. So I like your way of doing it. Maybe you did it the way I was just suggesting too. You could rewrite that as sine squared theta times 1 over cosine squared minus 1, right? And then that's sine squared theta times, that's secant squared minus 1, which is tangent. So either way, I don't know. They're both the same level of difficulty, maybe. Which one? From here to here? Oh, from here to here. Is that missing step okay? Does that help if we add that? Is that okay? Let's try another one. Again, multiple ways to do these, right? Like I said, actually, this is the way I thought she was going to go, but she did. Huh? That's what she did? Okay. And maybe there are other ways to do it too out there. So whatever. Whatever is correct is fine. Okay. Let's try another one. Yeah, I'll give you 30 seconds to start.
No idea.
More struggle? Bye, Siri.
Bye.
Bye, Siri.
Okay. I'm a little stuck right at the beginning, aren't I? Right, like so. There is one of the strategies that that would help here, and that's maybe strategy number 4. I don't know. Which side did you start with, Rick? Okay, just for fun. And arguably, it's almost it's pretty obvious that either one is going to be equally difficult here. So just for fun.
And then I multiplied by 1 minus cosine of x over 1 minus cosine of x.
Yeah, and that's like once you hear that, it's like I see where this is going. Right? Just stare at that for a second and see why that's really fruitful for a couple reasons. One is because I told you in tip number 4 that like setting up a minus b times a plus b is like a nice way to go because you're going to get in the denominator something nice. You're going to get like a 1 minus cosine squared. You ever see where that's headed? And then the numerator, it also makes sense maybe to introduce a 1 minus cosine, given that we're trying to get to this, right? So I already have 2 kind of strong motivations for doing that, even though at first that might seem like a crazy move out of left field. Do you see the rest? Like I said, sometimes these proofs have like a key that unlocks them, right? That was it right there. That was the key. So up on top, I have sine x times 1 minus cosine. On the bottom, I have 1 minus cosine squared. Notice I chose to multiply out the bottom, but not the top, because, you know, I'm just going to factor it again here in a second. So this is sine squared, and then the result follows, doesn't it? But again, this is the big move right there. All right, can I just send you with this one away? Just write it down, and then you can do it like in English class. Okay. History class.
I already have that class. I'm stuck.
To the 5th, yes. You'll be fine. All right, homework 2 tonight. We're going to spend today and tomorrow on proof on the same subject here, proving this stuff. So enjoy. I think you'll find it to be therapeutic. Is what I think you'll find. Like I said, you'll look back on this with very fond memories. Ask a friend who's already taken pre-calc how they feel about trig identities. You'll hear that